of the seminar, the research seminar of Modeman. And today we have this very special guest, Luca Calatroni, which is, as I usually said, a friend of ours, a friend of house, a friend of Modeman. And it's a big pleasure that you, Luca, have accepted our invitation. It's a big pleasure to have you here, at least this virtual setting. Fortunately, I hope like in a couple of months, everything is going to normal, or at least a new normal. And of course, you can come here again in person, which will be a big pleasure again for all of us. Today, Luca is going to talk about these generalized FISTA algorithms for complex optimization. And well, thank you again, Luca. The Zoom and this small auditorium is yours.
Thank you very much, Sergio. It's a pleasure for me being here. It's an honor actually for this invitation. So yeah, I missed already the chance to come back to Ecuador twice. I think there was like well, the IFIP was the most recent one. There was another one a couple of years ago when Costas could come, but I unfortunately couldn't. So yeah, I really look forward for the IFIP conference. But yes, as you said, I hope that in 2022 there will be a chance to visit you again, because I would really like to get back to Modemat. So yeah, please also make me aware of the time, because I believe I'd be kind of overrun. I practiced the talk and I think it's a little bit too long. So whenever you see it's getting too long, just give me a sign and I'll try to catch up. So I'll be discussing with you today this generalized FISTA type algorithm that we developed in collaboration with Simone Rebegoldi for dealing with convex and strongly convex optimization problems. So I start with a very gentle motivation because I'm not sure how familiar you are with FISTA type algorithms. So I start to introduce them like in my first slides. So generally, this type of algorithm is used to solve variational problems in a structured composite form, which looks like this. And this is the sort of form of problem that you end up with when you deal with the general formulation of an inverse problem. So you can think about, for instance, an additive type structure where you observe some measurement data Z, for instance, a noisy image, a noisy and a blurred image. So, and you want to retrieve your X. So X is going to be your unknown, and you have an operator, a linear operator A, which models, for instance, in the case of deblurring, a sort of a convolutional operator. So in a discrete setting is a sort of structured matrix, but you have to think of like a convolutional operation in a continuous world, and you have some noise. So, like, you know, by using standard maximum posteriori estimation, assuming some specific noise statistics on your noise and some prior knowledge on your solution, it's very common in inverse problem scenario to end up with a formulation that looks like this. So you want to minimize a functional in a solution space, capital X, which is the sum of two terms. So I'll be using the red color coding for denoting data fidelities in the following, and blue to denote regularization terms. So data fidelity for what follows would be typically assumed to be smooth. And for the prior functional G, we will assume no smoothness, which is actually what happens in most of the cases. So for instance, like a specific instance of this problem is the well-known Lasso problem, where you assume, for instance, Gaussian statistics. So you have a quadratic data term, and you have an L1 penalization on your solution. Some other examples are the elastic net, where for the same data fidelity, you have a sort of combination, weighted combination of L1 and L2 square regularization. As you possibly are all aware of, there is also the well-known total variation regularization model, for instance, for Gaussian image deblurring and denoising. So you have still like a quadratic fidelity and in a discrete setting, the L1 norm of your gradient. And you can consider also the other extensions, like for instance, higher order regularizations, and so on and so forth. I mean, you name it. It's you can consider, for instance, smoothed L1 models for better dealing with salt and pepper noise, so like impulsive noise, Kullback-Leibler divergences, whenever you want to deal with Poisson noise modeling, and more complicated data terms and more complicated regularization. So this is just to give you an idea of like the general form that these problems have. So now let's move to the abstract setting. So we'll be just considering general F and G in an infinite dimensional setting. So we have an Hilbert space and that with some norm. And for simplicity, for the moment, I'll be just not dealing with the regularization parameter lambda that you have here. So somehow will be just included in G to simplify notation, which you will see is a bit messy already. So as I said, we'll be dealing with smooth data fidelities. In particular, we'll be considering C1 smooth fidelities with Aleph Lipschitz gradients, so satisfying this inequality. Whereas for G, we'll be considering convex lower semi-continuous, but generally speaking, non-smooth penalties with, let's say, with associated proximal map defined in this way. So this is like the standard definition of your proximal point, which in the case of convex function G is not necessarily smooth, but convex makes the functional here that you're trying to minimize strongly convex, so that this argmin is uniquely defined. So here you really have an equality. So this definition is well posed. And also, yeah, here I haven't written, but we'll also be dealing with the convex functions F. So the problem is convex, but non-smooth due to the presence of the non-smooth component G. Okay, so a classical strategy to deal numerically with the non-smoothness, but by exploiting though the structure of smooth plus non-smooth term that your capital F functional has, is the so-called forward-backward or proximal gradient algorithm, which starting from an initial guess x0 and for a fixed time step tau, depending on the inverse of your Lipschitz constant LF, iterates this scheme. So what is the idea is that when looking at the smooth components, so the red components associated to F, you have a simple gradient descent, which is written inside the argument of your prox, which is used to deal with the non-smoothness in a typically efficient way whenever your prox can be expressed in a sort of analytical and closed form. Not necessarily, but let's say for many regularizers, for instance, like the L1 norm, this is the case. So eventually you end up with a sort of quite efficient expression. Okay, so let me just mention a few algorithms that are associated to the models that I described before and which deal with these type of iterations. A very popular one is the so-called ISTA algorithm, where you have quadratic data fit and L1 type regularization. Projected gradient descent, whenever you have your favorite smooth F, and you want to project your solutions on a closed and convex subspace Y included in your solution space X, so that the G becomes simply the indicator function of the set. Projected Landweber, when you specify also the form of F, so the quadratic fidelity, and alternative projections when you have also further subspace Z, which is included in X. So those are like pretty well-known and standard algorithms that, like in a general setting, can be expressed in a proximal gradient form. So what do you know about the speed of convergence of these algorithms? So again, in the same condition as before, by denoting with X star one of the solutions of this minimization problem. So let me remind you that we are dealing with convex problems, typically not strongly convex, so that the set of solutions may be not a singleton. So you may have multiple solutions. So that's why you have here an inclusion, but we are sure that this solution exists with the convexity. So when you look at like the speed of convergence in function values of the sequence of iterates xk to x star, you have this bound, which depends on a sort of constant that you cannot able to compute because it depends on the solution x star. It depends on the time step, but mostly depends on 1 over k. So if you are familiar with gradient descent algorithms, you realize that this is the same speed of convergence of gradient descent, which is typically very, very bad, very slow. So why FISTA was born? FISTA was born to somehow improve this convergence speed in a way that matches the lower bounds that was shown to hold by Nestor, for instance, in this book, and is of the order of big O of 1 over k square. So let's say there is a sort of a gap between the speed of convergence in function values that you get with this proximal gradient algorithm and the, let's say, least speed of convergence that you can achieve, which was shown to be 1 over k square. So is there any way to modify a proximal gradient algorithm so that you go towards like your faster bound instead of the larger one? And the idea is to introduce inertia. So just to give you a sort of a graphic interpretation of that, so if you denote by xk the sequence of iterates that you compute by using your proximal gradient algorithm, the idea is that at step k, instead of just moving toward the direction, toward this direction, you somehow exploit a little bit the direction which is drawn by looking at the distance and the difference between xk and xk minus 1, so that you somehow add a term which moves along this direction and on which you compute all the ingredients that were computed before, for instance, gradients, okay? So this sequence is a sequence which is not part of the sequence of iterates. That's why it's called extrapolated sequence, because you extrapolate it from the sequence itself. And you see, like the ingredients of FISTA are pretty much the same. So you still have a bound on your time step. You have some initialization. You have some parameters that need to be initialized and updated along the iteration in an explicit way. But through this update, which takes into account the inertial behavior that I described before, then you can simply iterate basically the same scheme as before, just applied on yk, so on the extrapolated sequence. And the good news is that if you go through the sort of convergence proofs, you end up with something which is much faster. So actually, it matches the sort of 1 over k square bound that I described before. And there have been like a number of studies on distance, for instance, on the convergence, not in function values, but of the sequence of iterates itself towards x star, like to refining the bound, not to big O of 1 over k square, but like to say small o of 1 over k square. And there is also a very nice interpretation which was studied and is being studied by Diatouche, Juan Tecuque, and co-workers that basically sees FISTA as a discretization in a suitable sense of some ordinary differential equations. And I think this is very interesting because it gives a new perspective in the sense of dynamical systems. So now, in the title of my talk, I mentioned also strong convexity, which is a stronger property than convexity. So just to quickly remind you what it means. So graphically, we have to think of strong convexity as a property which enforces my function to have a sort of quadratic bound with respect to its growth, right? So whenever we write the sort of convexity equality, what you end up with is something that looks like this. But in the case of strong convexity, you have an additional term, this red term, which is quadratic, and which gives your function somehow a little bit more of smoothness, if you want to think in this way. So we're not really saying that the function is smooth, because generally speaking, we are not really differentiable, but you may have like a growth which is like more regular than the one that you have with simple convexity. And why we studied like strongly convex variant of distance, because it was shown in this paper by Chambolle and Poc that whenever you can encode, you can have, whenever you have like a given information on the amount of strong convexity of your composite function, so either on your component F or on your G, then actually the rate of convergence become linear, as it is called in this framework. So actually it depends on K in this way. So it depends on K in terms of like a quantity, which is smaller than 1 to the power of K. So it's much faster than like 1 over K. 1 over K square goes like to converges much faster. And this is in the case of simple plain, let's say forward-backward algorithm, which encodes directly strong convexity. And again, you have a lower bound similarly to the 1 over K squared that I mentioned before in this case, which is a little bit of the order omega to the power 2K. So somehow the idea was again to define an algorithm similar to FISTA that could match this bound, that could enforce like linear convergence, but like in a faster way. So this was proposed by Chambolle and Poc. So the ingredients are really like similar to the ones that I'm going to present in the following. So we will be defining as mu the sum of the strong convexity parameters. So you may have either F or G to be strongly convex, and then you need the quantity that depends on this strong convexity parameter. And basically the idea is that you define an analogous scheme to FISTA, where now the red terms are the new terms that have been added with respect to the update rule of FISTA. And somehow you see it's very similar. So whenever you have no strong convexity, so whenever your problem is simply convex, so your mu is equal to 0, then your Q gets also equal to 0, and then you retrieve the standard update rules of FISTA. But whenever you encode specifically the knowledge of strong convexity, then, yeah, although it's a little bit hard to see here, but you see that your rate of convergence, which is this RQ, depends on quantities that decay much faster than 1 over K squared, decay like exponentially. So your rate of convergence is linear. And again, you retrieve the standard rate of convergence of FISTA by simply observing that whenever you put Q equal to 0, the mean of the mean between these two quantities is this one. Okay. So now let me point out a few things that sort of typically prevent practically the good performance of FISTA in the FISTA type of algorithms in many problems. So first of all, in all these convergence statements, I'm looking at step size which are constant and whose size depend on the inverse of the Lipschitz constant associated to the gradient of the smooth component. So this is not always no, or very often actually this can be estimated, but oftentimes it is estimated in a very pessimistic way. So this estimation is very large and then your step size is very small. So you practically end up with like quite slow algorithms. Also, we are dealing with proximal point computation. As I mentioned before, in some situations like the L1 norm, you have closed form solutions. But for instance, if your regularizer is the total variation, then there is no closed form for TV proximal points. So you need to have an inner solver that computes this argmin like a little bit imprecisely, so in an exact way. So is there any way to encode this inexactness in my computation? And also, and this was a little bit, let's say, for fun, but we saw that practically it really helps. Is there any way to incorporate in your sort of accelerated algorithm some sort of Newton type information in order to get some sort of Newton type updates to speed up efficiency even more? So let me start with the first drawback. So this is the case of a smooth optimization problem when you want to minimize a smooth function, which has a minimum here. And here I am showing two different scenarios. The one on the left, which shows what happens when I minimize my function by taking step sizes which are too small. And you see that you end up having a unnecessarily big number of iterations, although, you know, here you could just somehow go faster towards your minimum. And on the right, you have like a specular situation where you instead, when I'm showing you what happens when you have step sizes which are too big. So if they are too big, you may end up having, let's say, a move, an iteration, which corresponds to a point where your functional is not decreased. And in the attempt of decreasing it with step sizes which are too large, you might end up just bumping through, you know, between these 2 points and not converging. So one idea to mitigate to this problem is to consider, let's say, Armijoo-type backtracking step variations, where you start with an initial step size which you assume to be big, and then depending on some condition, you either keep it constant along your iteration or you decrease it whenever it's too big. So somehow, when at the beginning you start very far from the optimum, you go fast, and then whenever needed, you refine your iteration step by taking smaller and smaller step sizes. Okay, so this type of monotone backtracking was the one considered also in the original paper by Beck and Teboul. So as I said, is a monotone backtracking strategy. So your step sizes either stay constant or decrease. That means that whenever you have an initial guess, which is very bad, for instance, which is too small because, for instance, your Lipschitz constant was badly estimated, then there is no way you can actually go over it along the iteration. So you cannot increase the size of your step size. So by taking inspiration like to some adaptive backtracking strategies that were proposed for the convex case in this paper by Katja Scheinberg and co-workers, recently with Antonin and Chambol, we proposed a sort of adaptive backtracking strategy that somehow encompasses this convex case, but also deals explicitly with the strong convexity. So there is a sort of control that you have to make at every iteration that I'll be described in a second that allows you to increase wherever needed your step size. So what about inexactness? I mentioned this as another issue. So the proximal map, as I said, is not often available in closed form. So you need to approximate proximal points by means of capital N iteration of inner routines. So in this paper by Beck and Teboul a few years ago, they are looking at a TV deblurring problem. So TV and blur operator as the one motivating your inverse problem. And what you see here is the cost functional associated to the iteration of a FISTA type update, where the different colors correspond to the different number of iterations that you use to stop your computation of proximal point. Okay, so here we have TV, we don't have a proxim closed form, and you see that whenever you make at each outer iteration, at least let's say 5 iteration, I would say 5, your functional decreases. But when you take this number to be too small, you may even prevent your algorithm from converging. Okay. So it was shown in like some more recent works that in order to ensure the 1/k² rate of convergence, there must be a sort of accuracy that increases along the outer iteration in order to control these errors. Otherwise, they will accumulate and your convergence would be lost. So how to explicitly, let's say, include these in our analysis and in our practical computations. And about the sort of Newton type scaling that I mentioned before, that was an idea of my colleague Simone Rebegoldi from University of Florence, who has worked in the past on analogous, let's say, scaled type FISTA algorithms, where the scaling you will see in a moment. So I think it's more practical if I show you what I mean by scaling here. So affects, let's say, the distance appearing in the definition of my proximal point. So instead of taking the standard, let's say, Euclidean norm, you take non-Euclidean norm depending on some symmetric and positive static matrices D, which have like some ordering relations, which is defined here. In particular, you want the norm induced by D to be bounded by like some constant by some let's say multiple of the identity, let's say, of the Euclidean norm. And why the idea of introducing this scaling? Because in the context of smooth optimization, so whenever you don't have to deal with proximal points, it was shown that scaling somehow the gradient was producing results that were comparable to what you would get by means of a Newton type, so second order schemes. But here I recall you, we are dealing with just first order optimization. So it's kind of interesting that you could improve even further your convergence by simply introducing some scaling. Okay, so what you have to remember then in the definition of scaling is just the fact that what changes is the definition of the norm here. Okay, and just as a matter of notation, for like a subset of my solution space, and for like a symmetric and positive definite matrix with some with this ordering relation, I'd be defining PYD as the projection over my set Y, depending on this scaling matrix D. Okay, so now it's time to introduce the algorithm that somehow looks a little bit complicated, but is capable to deal with all these sort of different issues of FISTA. So it deals with strong convexity, it deals with scaling. It is capable to adjust at each iteration the size of the step size, possibly also increasing it. And it explicitly takes into account the computation of proximal points. So we call this algorithm somehow, like in a funny way, like SAGE-FISTA, because there were like many issues that we detected in FISTA. So we thought about a SAGE, a wise way to deal with them. And that's why we ended up finding this acronym. So just to give you a little bit the details of, I'll be quick on that because it's a bit too technical, I think, but just to go a little bit in the detail of the different ingredients. Regarding the adaptive backtracking strategy, we use the similar idea as the ones that were shown, for instance, in our previous work with Antonin. So here we were dealing with like an algorithm where there was no inexactness, no scaling. And the starting point of the analysis of these FISTA type algorithms is the fact that you need to write down a sort of descent condition that guarantees that each iteration, your functional decreases, or like a functional plus something decreases. Okay, so this is the sort of inequality you end up with. And this inequality depends on this orange term, which somehow to create a recursion you would like to neglect, and you would like to stay always greater equal than 0. So it depends on what is called the Bregman distance between these 2 points, so the new point and the extrapolated point, and also on your step size. So to guarantee descent, you need to guarantee that this term stays positive. This is true, for instance, when you take your step size to be constant and smaller than 1 over LF, you can show this. But this allows also for like on-the-fly checks of these inequalities. So instead of fixing your step size, you can check basically at each iteration whether this is negative or this is positive. And you know, if it is positive, but your step size is bigger than this, that's okay, because that's the only thing that you need to impose your descent. So that's how you end up with a sort of adaptive backtracking strategy. You can do the same whenever you incorporate scaling. So the scaling that we incorporate is variable, and I'll be showing you how it's variable. So you have to think about a sequence of matrices that gets updated along the iterations. So here you have basically the same inequality as before, where you have like scaled quantities, and you have, with respect to here, where you have the strong convexity parameter, some sort of strong convexity parameters that express strong convexities with respect to the matrix that you have introduced here, so your decay. So the sort of forward-backward update that you deal with in this context looks like this. So it's this kind of similar to the one that I described before, where you have prox and gradient descent, but there are also some scaling matrices that appear here in the evaluation of your non-Euclidean norm, and here the inverse in the evaluation of your gradient. And again, these parameters here express strong convexity with respect to these non-Euclidean metrics. And about inexactness, I'll be quick on that. The thing is that by introducing a suitable definition of inexactness, you can somehow retrieve in your descent inequality some terms that accumulate, of course, along the iterations, and which you need to control to make them summable in particular, so that you can still guarantee descent. So what is the notion of inexactness that we use? This is pretty standard. It was introduced in these two papers, which are very, very nice because they explain in a convex setting, in a convex analysis framework, like all these sort of more optimization related notions. The idea is that basically, if I define the functional h in this way, so this is the functional that allows you to express in a very compact form the forward-backward iteration that I described before. So these forward-backward iterations. So when I minimize this, I'm actually writing one step of like the forward-backward scheme, right? So in particular, if I'm thinking of not being able to compute the proximal point, which I call here x at k plus 1, because of inexactness, I called xk plus 1 an approximation of x hat k plus 1 of accuracy epsilon k plus 1, a point such that whenever I evaluate this functional h in xk plus 1 and I take the minus the 1 ideally I would have to compute, this accuracy is equal to epsilon k plus 1, right? So I'm sort of saying I resolve this optimization problem up to some precision. Okay, so just let me show how the extrapolation rule changes. They are very sophisticated, but don't worry, I'll explain in a second that they are not so bad. So this is the FISTA type rule that I mentioned before. And this is how the SAGE-FISTA extrapolation rule becomes after having all these. And it depends on many parameters, which are all you know, either automatically estimated along the algorithm, for instance, the step size, these strong convexity parameters, which with respect to the non-Euclidean matrix are also somehow adjusted automatically. So although it looks like very parametric, there are not so many parameters that you have to tune. And of course, if you forget about the red terms, you end up with the standard FISTA rule. And whenever you have, you know, no strong convexity, that's just, but this is nothing but FISTA. Whenever you don't have strong convexity, but whenever you allow, let's say, for adaptive backtracking, then you end up in the same sort of adaptive rule of backtracking that we also had with Antonin, and which was proposed for adaptive FISTA in this paper. Okay. So this is the algorithm. So, you know, I've basically given you already the main idea, so I won't go too much into the detail. The thing about the step size, which I think is interesting, is that what you do is that at each outer iteration of your algorithm, you have set up some scaling parameters, okay, and define them in an appropriate way. But what you try to do at each iteration is to increase your step size. So you divide your previous step size by a number delta, which is typically smaller than 1 or equal to 1 in the case when you just keep it constant. But you try to increase it, and then you do your sort of, it looks pretty weird, but it's the sort of generalized version of FISTA in this new setting. And then you compute like all the quantities that you need to check this control on the Bregman distance that I introduced before. So if this is verified, then it's fine. Then you can keep your step size bigger than the one that you had before. If it is not verified, then you have to decrease it. Then you decrease it by a factor rho in a standard Armijoo, in an Armijoo fashion. Okay, so just to give you an idea, there are some technical assumptions on D, which I will just give you a graphical representation of this. So in our examples, we are taking these non-Euclidean matrices to be diagonal so that they are easy to implement numerically. And you have this assumption to verify, which generally speaking has to be interpreted in the following way. Basically, you start with a scaling matrix which is close to the Hessian matrix of your problem. And then this matrix along the iteration will be squeezed towards the identity. So you have diagonal entries that along the iterations go closer and closer to one. So basically you benefit of this variable scaling in the early iterations, and then in the late iterations, you are just, dealing with a standard gradient type algorithm. So this is the result. This is the result in terms of rate of convergence, which looks horrible, but which is just satisfying due to the fact that in this very complicated and involved setting, we could still prove these. So the fact that depending on the strong convexity parameters, the backtracking parameters, and the scaling parameters, you still have a sort of fast decay whenever your strong convexity parameter is larger than 0. So whenever this is 0, this becomes just 1, and then you end up with a rate which is similar to the one for FISTA, but generally speaking, you have faster rates. So I skip this and I show you some examples. So the examples that we looked at come from the world of Poisson type inverse problems, where you deal with images Z, which are like the blurred and Poisson degraded version of your X that you want to retrieve, and you have also some background. Okay, so it's pretty standard. Possibly you all have the feeling that when you write down in a statistical form, in a Bayesian form, the ingredients of this problem, and you do standard maximal posteriori estimation, you end up with a data fidelity term, which is the one typically associated with Poisson modeling, which is the Kullback-Leibler divergence, which looks like this. You want to enforce, generally speaking, in a Poisson scenario, a non-negativity constraint. So you have an indicator function in this set. And then you have non-smooth regularization term. I'll be showing you two results. So I keep it general for the moment, but yeah, so regarding, I won't go into the detail because I'm running already a little bit out of time, but just to give you an idea, the way you define the scaling was pretty standard. So actually you take inspiration from the so-called split gradient strategy, where the idea is that you decompose the gradient into two terms and you define your diagonal matrices in this way. That was shown to improve the speed of convergence in a smooth optimization setting. So we basically use the same. And to define the threshold parameters that get updated along the iterations and converge to 1, so that your matrices converge to the identity, we use this update. So you have two parameters to choose. One that somehow drives the early iteration update, while the late update gets driven by S2. And here I really don't want to spend any time on that, but if you're interested, I can send you the slides. There are routines that are able to compute to guarantee the fact that whenever you pick an accuracy epsilon k plus 1, and you are dealing with the computation of this type of iteration, your proximal point gets computed with an accuracy fixed, like this epsilon k plus 1 accuracy. To deal with that, you have to design some suitable dual fast solvers which have a control on primal dual gap, and they can be quite general. So the regularizer can be quite general. So we use some standard routines that are able to guarantee that the proximal points can be computed are a suitably good approximation of the one that we cannot compute because it is a solution of an inner minimization problem. And of course, this is unneeded whenever we have prox in closed form. So the first validation result was a little bit easy because we didn't want to include just to start with strong convexity, nor inexactness. So we wanted just to look at how the scaling and adaptive backtracking works. And the test problem was this one. So we used as a regularization some standard L1 regularization plus some non-negativity constraint, and a fidelity term that has been used previously to model in an easier way sort of Poisson-type statistics. You can find this by developing the Kullback-Leibler divergence using Taylor expansion around the noisy data, okay? So it's a sort of weighted L2 fidelity, which somehow encodes some signal dependence. We have this scaling, and we apply this to the problem of image super resolution. So the operator A here is actually the product of a undersampling operator and a blur operator. So we have like some background, we had to choose some regularization parameter, and we had to choose some backtracking parameters. So for instance, an initial guess for my Lipschitz constant, you know, an Armijoo parameter, the one that is able to decrease my step. And for fun, we picked delta, so the parameter that controls how much you try to increase your step size, either to equal to 0.99 or to 1. So whenever is equal to 1, let me just remind you that you take your step size constant. So you are doing a classical Armijoo-type backtracking. When you take it slightly smaller than 1, you try in every iteration to increase it a little bit. And let me show you that here the idea of backtracking is interesting because when you want to provide an estimate of your Lipschitz function at f, that depends on many things, but in particular on this quantity here, 1 over the max of zi plus b, which in the case of very small background becomes very large. So actually your estimate may be very bad. Okay, so here are some results. So just to give you like some information on how to read these graphs. So the first row refers to graphs obtained using scaling, but Armijoo backtracking, so standard monotone backtracking. The ones in the second row, when you use adaptive backtracking. The blue lines correspond to the solution that you obtain by using standard FISTA. So whenever you don't include any scaling or any backtracking, and you see here that in the first row, when you use Armijoo, generally speaking, and scaling for different choices of the thresholding parameters, your convergence is faster. But it gets even faster whenever you update your time step. And you see it here. So here on these two graphs, you see the evolution of the local estimate of your Lipschitz constant, which is 1 over the inverse of the step size. So in the case of monotone backtracking, as tau k is 1 over lk, your lk can only increase, whereas here it can increase or it can decrease. And whenever it's small, that means that your time step is very big. So you're going very fast to the optimum. And if you compare the y-axis here, you see that like in like, I don't know, 300 iteration, we reach like a much better accuracy than the one that we get with standard backtracking, and over also a fixed CPU time. So just to conclude, we also did some tests really including strong convexity. So that has a little bit more involved. So the fidelity here is the Kullback-Leibler divergence. As a regularizer, we use total variation, so the L1 norm of the gradient, in order to deal explicitly with the inexactness. plus also some quadratic perturbations, so that our G here is really strongly convex. And basically same test as before, same choice of scaling as before, and same comparison between backtracking and Armijoo, with a bad estimation of LF, again, due to the fact that you need to divide by B, and when B is small, that quantity becomes very large. So your sum step can be extremely small. So you see again, the comparison between the blue line, which is the standard FISTA, and the sort of red and black lines, and in particular, the advantage that you have whenever you choose an adaptive backtracking strategy combined with the scaling. So you see here that the y-axis have very different range, and in particular, the estimate that you find by using this expression does not get updated, cannot be updated using a standard backtracking, but it can be updated using adapted one because you allow your Lipschitz constant to decrease. Okay, so just to conclude, this algorithm encodes several features, so it's a little bit involved even to explain. It's very complicated, but let's say it's a unified version of like a FISTA type algorithm, including scaling, adaptive backtracking, and explicit, let's say, computation of inexact proximal points in case of convex and strongly convex optimization. So what would be interesting to look at is the fact that, typically speaking, so we don't typically have an estimate of mu f or mu g. So the strongly convex parameters typically are unknown. So it would be nice to find some techniques able to sort of provide an estimate of these parameters, because we saw, as I shown you, that whenever you include this quantity explicitly in the algorithm, your rate becomes linear, so you gain in convergence speed. And also maybe to replace the sort of strong convexity condition, which is stronger, with like some weaker conditions like the Poilievre-Clausius condition. And so this is all I had to say. I just stopped with an announcement that I hope will be the chance to see you all maybe in Europe at some point. So together with some colleagues from Italy, we are organizing the 9th edition of the Scale Spate and Variational Methods in Computer Vision Conference, which will be in 2023, in May 2023. So we have already like dates, 21, 25 of May. It's a pretty nice conference. I don't know if you've been there, but it's a small community of people which, you know, typically come from Europe, but not necessarily. So maybe you will be interested to come, especially due to the fact that we'll be organizing it in Sardinia in a beautiful resort, which is like, I don't know, 50 meters far from the beach. And scientifically, it's nice because it allows the publication of conference proceeding in a Springer lecture notes to computer science, and invites also the best paper to contribute to special issue of Journal of Mathematical Imaging and Vision. So I'll be giving you details as soon as I have them, but I wanted just to give you the dates at least. So sorry if it took me too long, and thanks for your attention.
Oh, thank you, Luca.
Thank you.
Okay. And I'm sure there are a lot of questions, so it's time for questions.
Oh, David,
okay.
I see. Yeah.
Thank you, Luca, for such a great talk. It's quite amazing, the work you've done with you guys. I have a question related to the deep matrix that you're using for scaling.
Yeah. Yeah.
You're assuming it to be a diagonal for certain applications, and
yes,
it doesn't actually take any structure from the problem itself, right?
So there are many ways you can choose this metric. So there are like, we decided to choose it as a diagonal matrix because in this way, whenever you numerically deal with it, you simply have to deal with pointwise, you know, add products. So it's very easy. But there are like other strategies. The one that so I didn't have the time to go into the details. So this strategy actually depends on the structure of the problem, because it exploits a decomposition of your negative gradient. So your f, of course, is specific for the problem at hand in this form. So you have basically to decompose your negative gradient into the difference of u and v, being one non-negative, one positive. And then, and that was, you know, taken from previous work on scaled gradient descent approaches for smooth optimization. So we simply adjusted them to work even in the non-smooth case, but the choice of decay then is this one. And you see the V that is a little bit hidden here is the one that comes from this decomposition, so is related to the specific problem at hand. Just to give you a little bit more of an example, yeah, here I have written the decomposition. So for instance here, yeah, it relates to the adjoint of my blur matrix.
Okay, that's great. And have you thought, I mean, I don't know if it makes sense, but exploring other possibilities for the D update, for instance, I don't know, at second order DFGS?
Yeah. So, yeah, exactly. So that, we did some tests. Right, so we didn't explore too much like this, but I really think would be interesting. What we tried to do was somehow for I believe it was for this problem, yes, just to compute. So it's a quadratic problem, so it was easy to compute the Hessian, and just you know, as a proof of concept, keeping as constant d the Hessian associated to this term. And we saw that, you know, it was converging as fast as the Newton method eventually. The problem being that, of course, it gets very fast because, so it's a little bit hidden here, but generally speaking, there is an interplay between the updates of the scaling matrices and the precision that you need to solve your proximal points. So actually for this specific problem, since your proximal point is like in an explicit form, I think you can do this. You can use a BFGS update, the Hessian, it won't be probably too bad. But for instance, if you take total variation, then, you know, as the iterations increase, you need to solve the problem more and more accurately. And you have like a sort of big matrix to use, so it's a sort of not very well conditioned, and that gets, you know, that gets very slow. So eventually, if you just look along iterations, the speed of convergence is wow, is super fast, but it gets like much more time. So BFGS could be a solution. We didn't try that, but I'm sure it would be nice. The advantage here is that after, you know, depending on the choice of your, these S1 and S2 parameters, your Hessian type matrix becomes close to the identity. So you don't have any problem of like bad conditioning anymore. And then, you know, whatever you gained in the early iteration, that's okay. But then in the late iterations, you just do standard first order FISTA. Yeah.
And so, you can take advantage of these limited memory sparse structures of BFGS updates, right? Or it doesn't make sense?
Yeah. I think we can. We haven't done it, but I think we should definitely. So
worth exploring.
My worry about this would be that you know, I don't know how these matrices. So because in BFGS you would rather start maybe, I don't know, from the matrix, from the identity matrix.
I'm not sure the limited memory FGS. I'm not sure about the limited memory FGS because the BFGS matrix has the advantage that you have an explicit formula for the inverse, but you don't have it this way.
That's correct. Yes.
Yes, that's true. That's true. Because we need to compute this.
That's right.
That's true. Yeah. So yeah, true.
Probably
actually, this
there's
is
a
what
way.
makes that's what makes when you take the Hessian computations extremely
Heavy, yeah.
Yeah.
But great work otherwise. I mean, it's quite,
Thanks.
quite
Yeah,
amazing.
thanks for the questions.
Yeah.
There are more questions or comments? Okay, if it's not the case, we want to thank Luca again. Thank you for this wonderful talk and
Thank you.
As we were saying, we will work in computer vision for doing these 2 years just to go to the
Please do. Yes, it
That's complete a motivation.
I mean, Sardinia seems like a good motivation for me.
I think, yeah, especially like the edition that they have of this conference this year was also supposed to be in a very nice place in France, close to the beach, but then they had to do it virtual. So when we announced this, there was like, you know, like a big of wow, because people were so happy of, you know, catching up of like a 2 year. So yeah, please do. And I'll be giving you details as soon as we have more. So far it was just a project, but we start soon working on that.
Perfect, thank you. So thank you, Luca. Thank you all for being here, for being in Zoom. And see you next week. Thanks. And
thank you again.
You guys.
Bye. Nice afternoon. Bye.
Thank you, Luca. Bye.
See you guys.
Bye.
Luca.
Thanks
Bye.
again. Bye bye.
Have a good
Bye
one.
bye.